Have you ever fired off a quick document to a printer down the hall, or maybe transferred a large file to a coworker, and just kind of marveled at the fact that it never accidentally ends up on someone else's screen? I mean, how exactly does a network switch know which device is yours among literally millions of possibilities on a network?
Well, welcome to This Explainer. Today, we're taking a pretty fascinating journey under the hood of local network communication. We're going to demystify this invisible, lightning-fast traffic system we call Ethernet. It's what keeps our modern world connected. And sure, it all happens in the literal blink of an eye, but as you'll see, there is a massive world of logic behind it. Okay, let's dive right into this. Our roadmap today takes us through the basics of Ethernet, then we'll jump inside the data frame itself, decode some MAC addresses, look at unicast, broadcast, and multicast, and finally, see how Ethernet switches actually learn.
All right, kicking things off with Section 1, the basics of Ethernet.
So to really wrap our heads around this, think of your local network kind of like a real-world postal service. Before a single letter can even be delivered, you need physical roads, right? You need foundational rules. Well, in networking, those rules are Ethernet. Defined by some very strict IEEE standards, Ethernet operates right at the absolute bottom of the OSI model, specifically the data link and physical layers. It honestly doesn't care about your web browser or your apps. It is the absolute physical foundation that's wiring your local network together.
And within that data link layer, Ethernet actually splits its job into two parts, which is super smart. First, you have the logical link control, or LLC sublayer, which acts like an interpreter, identifying protocols like an IPv4 packet, for example. And then right below that is the media access control, the MAC sublayer. This guy handles the heavy lifting of physical addressing. Now, fun fact for you, old school Ethernet used to be this chaotic Wild West with data collisions happening constantly. Just a mess. But today's modern MAC sublayer relies on full duplex switches, basically eliminating that collision chaos entirely.
Moving right along to Section 2, inside the Ethernet frame. Okay, so if Ethernet standards are the postal roads, the Ethernet frame is the actual physical envelope carrying your message, and its anatomy is incredibly structured. It kicks off with an 8-byte preamble just to get the devices perfectly synchronized. Then comes the really vital routing info, the destination and source MAC addresses. So literally the to and from on our digital envelope. After the type field and the actual data payload itself, the whole shebang ends with a frame check sequence, or FCS. This acts as a strict quality control trailer to catch any transit errors. Pretty neat, right? But, this digital postal network has some very strict sizing rules. The absolute minimum size for a valid Ethernet frame is exactly 64 bytes. If a device receives anything smaller, well, it's considered a runt frame, which, yeah, sounds kind of cute, but the hardware will automatically and mercilessly discard it. On the heavier end, the standard max is typically 15-18 bytes, though to be fair, modern networks can support much larger jumbo frames for those massive data loads. All right, Section 3, decoding MAC addresses.
Let's zoom in a bit on those permanent physical street addresses written on our envelopes. Every single device needs a permanent, unchangeable fingerprint, and this begins with what's called the OUI, or Organizationally Unique Identifier. It's this 24-bit code assigned strictly to hardware vendors by the IEEE. So whether it's a massive Cisco switch or just your everyday Apple laptop, their network interfaces start with a specific identifier. This is what absolutely guarantees that no two network cards on Earth share the exact same hardware address. Now, what's really fascinating about this slide is how elegantly that identifier fits into the grand scheme of things. The full MAC address is exactly 48 bits long, and it's split perfectly down the middle. The first half is that vendor OUI code we just talked about, and the second half is a completely unique value assigned by the vendor to that specific device. It's just a foolproof system for global uniqueness. So what actually happens when this perfectly addressed envelope arrives at a computer? Well, when a device receives a frame, its network interface card, its NIC, instantly checks the destination MAC address against its own physical address, stored right there in its RAM. If there's a match, awesome. It de-encapsulates the data and passes it up to the operating system. But if there's no match, it just coldly and efficiently discards the frame without a second thought.
Which brings us to Section 4, unicast, broadcast, and multicast.
Just like a real postal worker, our network has different delivery methods it can use. Most of the time, devices use unicast, which is just a simple one-to-one delivery straight to a destination. Simple enough. But sometimes a device needs to shout to the entire room. That's a broadcast. It floods the entire local network using a destination address made up entirely of Fs, literally FFF, FFF, FFF.
When a frame has that all-F address, every single device on the network is forced to stop, receive it, and process it. And then we have this very clever middle ground called multicast. Think of this kind of like a magazine subscription. A multicast frame is sent out, but it's only processed by a specific, defined group of devices that have essentially subscribed to that data. For example, IV4 multicast packets automatically map to destination MAC addresses starting with 01-00-5E. It's super efficient because it reaches a group without unnecessarily interrupting every single machine on the network.
All right, the final piece of the puzzle, Section 5, How Ethernet Switches Learn.
It's time to formally introduce the incredibly fast, invisible postal worker managing all this traffic, the Ethernet switch. Now, when a Layer 2 Ethernet switch is first powered up, it honestly has total amnesia. Its memory, called the MAC address table, is completely empty. It knows absolutely nothing about the IP addresses or the data payloads inside the frames. It strictly cares about Layer 2 MAC addresses. And to keep its routing map fresh, it dynamically drops learned addresses from its memory after a standard 5-minute refresh timer expires.
So the crucial point is, how does it actually overcome this amnesia? Well, it uses a brilliant 3-step process. First, learn. It examines the source MAC address of every incoming frame and records exactly which physical port it arrived on. Second, forward. It checks the destination MAC address against its newly built table. And third, flood. If that destination address is a complete mystery, it simply floods the frame out of all other ports just to guarantee it eventually hits its target. And that elegant logic is exactly how Layer 2 switches keep your local network traffic flowing perfectly, mapping physical addresses to switch ports in mere fractions of a second. But, wrapping up this explainer leaves us with a pretty fascinating puzzle. We've seen how local communication is entirely sorted by these hard-coded MAC addresses. But what happens when an envelope needs to leave your local street and travel the globe? How does data seamlessly jump from Layer 2 Ethernet switching to Layer 3 IP routing to connect with a server on the other side of the world? Keep that provocative thought in mind next time you log onto your home network. Thanks for joining me on this explainer, and I'll catch you next time.